You always hear that computers think in ones and zeros, right? But have you ever really stopped to wonder what a 1 or a 0 actually is? I mean, physically? Today, we're going to make those bits real. We're taking that abstract idea and turning it into something you can actually see and measure.
Yeah, this question right here, it's the whole point. We toss around words like bits and binary like it's nothing, but they're not just, concepts. Inside every single piece of electronics, they have a real physical form. So let's get down to it. What does a 1 or a 0 actually look like to the machine?
And boom, here's the answer. It's just electricity. Seriously, a logic level is just a fancy term for a specific voltage that a circuit is designed to understand. So for most systems, a high voltage, let's say positive 5 volts, that's a logic 1. And a low voltage, pretty much 0 volts, well, that's a logic 0. It's really that simple. High voltage is a 1, low voltage is a 0. That's the secret.
Okay, so to really see this happen, we're going to get our hands dirty. Well, virtually. This is our lab for today, the Digital Electronic Training Set. This thing is awesome because it lets us manually create those high and low voltage signals, and, this is the important part, see exactly how the machine reads them.
All right, first things first. A computer can't do anything until we give it some information, right? So how do we actually make a 1 or a 0? How do we create those voltage levels?
On our training board here, we're going to be using this bank of switches, the 12-bit data switch. This is basically our keyboard. Each and every one of these little switches has one job and one job only: send either a high voltage signal or a low voltage signal into the circuit.
And you know what? It couldn't be simpler. You want to send a logic 1? You just flip a switch up. That physically connects the circuit to a high voltage source. You want to send a logic 0? Flip it down. That connects it to the low voltage. And just like that, poof, you've made a bit, a real physical bit. Okay, great. So we flipped the switch, we sent the signal. But we can't just trust that it worked, right? This is engineering, not magic. How do we know the machine actually saw our up as a 1 and our down as a 0? We need to check its work. We need to verify it.
And this is where things get really interesting, because the answer isn't as simple as you might think. See, how a signal gets interpreted, it all depends on the design of the system that's looking at it. The very same voltage can mean two completely opposite things. And that brings us to this super important idea of positive versus negative logic.
Now, the cool thing about this training board is that we can see both interpretations happen at the exact same time. You see these two rows of little lights up here? One is our positive logic indicator, and the other is the negative logic indicator. Now get this, they're both wired up to the exact same switch, but you're about to see them tell us two very different stories. Okay, let's start with the one that makes the most sense to us, the one that feels, natural. Let's check out the positive logic circuit. So, the rule for positive logic is pretty much what you'd expect. Light on means 1, light off means 0. The high voltage from that logic 1 directly powers the little LED light. Simple, direct, one-to-one, no tricks here.
So let's walk through it. We find the circuit that says high-level LED indicator. We flip our switch up to make a logic 1, and yep, there it is. The LED for that switch turns right on. We've just confirmed our 1. Now let's flip it back down to logic 0, and the light goes out. Perfect. Exactly what we thought would happen.
But wait, that's only half the story. Now let's look at that other row of lights and see how a completely different system can look at that exact same switch. Time to check out the flip side? Negative logic.
Okay, brace yourself, because here the rules are completely backwards. In a negative logic system, the LED turns on to tell you it's a 0, and it stays off to tell you it's a 1. I mean, just let that sink in for a second. The light being on, the active state, actually means 0. It feels totally wrong, but I promise you it's a perfectly valid way to design a circuit. So let's try it. We look at the low-level LED indicator, we flip our switch up to logic 1, and what do we see? Nothing. The light is off. And that's because in this system, off means 1. Okay, now flip the switch back down for logic 0, and bam, the light comes on. The light turning on is the confirmation of a 0. It's the complete opposite of what we just saw. All right, let's just pause and recap for a second. We did one simple thing. We flipped a switch. That created one single electrical state, but we just saw it give us two totally opposite results depending on where we looked.
I mean, the difference is huge. In positive logic, a lit LED means 1. Simple. In negative logic, that exact same lit LED means 0. The light itself didn't change, it's just on. But what it means, its a logical value, is completely flipped upside down just based on the rules of the system.
This table lays it all out perfectly. Look, when we set a logic 1, that switch up, the positive light is on, but the negative light is off. Then, when we set a logic 0, switch down, the positive light goes off and the negative light comes on. It's a perfect mirror image of itself. So cool. So if there's one thing to take away from all this, it's this. A high voltage isn't automatically a 1. It's only a 1 because the engineers who designed the system agreed to call it that. The physical reality, the electricity, is separate from the logical meaning. And once you get that difference, you're on your way to really understanding how all this digital stuff actually works.
Think about it. We just controlled one single bit with one clunky switch. But the phone or computer you're watching this on has billions of tiny, microscopic switches flipping between high and low voltage millions of times a second. So the real question is, how do you go from this one simple on-off switch to running the complex software that's playing this right now? Well, that's the real magic of digital engineering. We'll talk more soon.